So, hello everybody. Today our speaker is Hoang Duc from the Institute of Mathematics in Hanoi and also of the Max-Planck-Institute for Mathematics in Leipzig. He shall speak on ergodicity of dynamical system under stochastic noises. Yes. He only did visit our seminar in before the COVID, right?
Yes.
And
Yes.
spoke on different things, but now it's the first time in Zoom. Yeah, please.
Yes. Thank you very much, Fan, for your introductions. And this is also my pleasure to give a talk at the beginning of 2023. This is
Louder. Can you?
Yes. Can you hear me now? Yes.
Yes.
So I have to stand a bit closer to the microphone. So yes, this is also a little bit challenging to give the first talk at the New Year's 2023. So my title is Ergodicity of Dynamical System under Stochastic Noise, in which I would clarify three keywords here about the ergodicity, about dynamical system, and also about stochastic noise. So when we talk about dynamical systems under stochastic noise, it means about random dynamical systems. And so we have to somehow construct metric dynamical systems, which is a base in order to introduce the concept of random dynamical system. And for that, the ergodicity of the metric dynamical system is very important problems which need to be solved. And so you're going to see the next slide. Okay, so here's the content. So I will start with some basic facts on ergodicity, classical results on dynamical system and ergodicity. So what is ergodic transformation or ergodic dynamical system, which is can be like in the continuous time or in the discrete time. And then I'll show you motivation examples in stochastic differential equations and explain to you why the ergodicity is a very key concept and key issue we need to solve in order to work with several important problems in stochastic calculus. And then in the next chapter, I'm going to talk about the very recent results, which we get related to rough path calculus and rough differential equations. So the specific question could be then how we can generate a random dynamical system and prove the ergodicity of such type of equations, which could be like section 2 and section 3. And in application, I would go back to the motivation example, but generalize it a little bit further with some result on random attractors, which include both for the continuous equation and for the discrete equations. So let me start with the basic facts. I suppose all of you know here with very textbook, classical text on dynamical system and the concept of ergodicity. But let me also browse through several key concepts. So you start with something like a dynamical systems, which is supposed to be like a probability space. So you have omega, you have a sigma algebra F, and you have a probability measure P. And we also have a transformation theta from which is indexed by time and also acting on omega, such that it is measurable, but it's also invariant under the probability P, and also it certifies the semi-group properties. So by this, it means that theta 0, which is indexed at the time t equal to 0, is the identity map at omega. And then theta certifies the semi-group properties as theta t plus s equals to theta t, and then acting on theta s. And theta is also p invariant in the sense that if you're acting for every subset of the sigma algebra F, then it is invariant under the probability P. So now we call theta is ergodic. If we normally have no such invariant set. In other words, it means that because you know the theta is from omega to omega, it means that trivially it would have invariant set of measure 0, which is empty set, and a full measure, which is our whole set omega. But if we assume that there's no other invariant set A, like theta t A equal to A for every t in the time set, then we call it theta is ergodic. Yeah. So this concept of ergodicity can also be relaxed a little bit by some crucial lemma. For example, you can prove that ergodicity can be confirmed if you can prove that theta is invariant with respect to modulo p, which means that if you have theta is has no invariant set with respect to modulo p. By this, I mean that for every a which is invariant, you have p of a and then intersect with theta t of a. You take the remaining set, which is the difference away from the intersection between the two sets, and suppose that the probability of that set is 0 for every t, then you can call that that A is invariant with modulo p. And if all this invariant set with modulo p has measure 0 or 1, then you can call that this is ergodicity. Another result on ergodicity is that there's a lemma which states that you can also easily check the ergodicity of the dynamical system theta by checking the intersection. If you starting with any measurable set A, and then you run it forward or backward with respect to the dynamical system theta, and then you intersect it with any measurable B set. You're taking the intersection, you take the probability, and then you take the average. Then the average in time is exactly the PA time PB. So it means that by averaging, you actually give some set which is somehow independent from B. You start with A, but then it is somehow independent with respect to B. And because of that independent, the left-hand side divided by PB is actually the conditional probability with respect to B, which is exactly BA. This is another way to say that, well, on average, A and B after the transformation of theta or acting of the evolution of theta would be independent. And that can be worked with any AB belong to some algebra, which is generated to our sigma algebra F. There's another important lemma, which is always used in stochastic calculus. And this is the lemma. I suppose that you can see my pointer here, which is the second lemma. It states that if you start with any measurable mapping T, and then you have a probability P, of course, then you can also transform that law of T into VIP by that transformation. So you have T also transform P into some probability measure, which is defined by this one. So now you can also check the ergodicity by the following. If you suppose that for every T belong to the time set, you can prove that there's a subset omega T of our space omega, such that if you going, I mean, theta T, and then you acting on T, or and the right hand side you also acting, but the other way around. You start with theta T and then you act on T. So it's something like cohomologous, right, or conjugate.
Yeah, such a push power measure.
Yes. So then you have to restrict on that cohomologies in the omega T. And if suppose you say that, well, there's a full measure set omega T such that these relations hold, then the ergodicity of our initial dynamical system theta will lead to the ergodicity of the transform system after the transformation T. So this is very important because you will see in the several coming slides that how it can be applied to stochastic calculus. It's turned out to be very, very fruitful. So you might, I mean, very well known on very classical example on the ergodicity, right? For example, you might see that, well, we toss a coin or we toss a die, and then for every moment we check whether or not the coin is head or tail, right? And then suddenly you can say that, well, if you have a very fair scenario, then the probability of having a head is 1/2, and also in the tail is also another 1/2. But you see that how can we construct that? In order to prove the ergodicity of this, we need to construct the probability space, and we need to construct a sigma algebra. And we also have to construct the measure. Now, for this very trivial example, we can this is exactly the Bernoulli situation.
Can you check a little bit slower because at the beginning? So you have taken the Bernoulli measure on the space of on possible. How to say? Half is a what is a
H? So you have this is because
now
you toss the coin. Then you can have the scenario either head or tail.
Yeah.
So it means that every xi is a result of the outcomes. The outcome can be head or tail, and you suppose that you would toss this infinitely times.
Yes, Bernoulli measure on the space of the unpossibles. How to say?
Yes. So all the scenario can be constructed. So every omega here, which is an element of our capital omega, would be an infinite sequence of xi in which xi either head or tail. And then for that you can, let's suppose that it's 0, 1, and then you can work with this space of infinite.
What is the cylinder sequence set here?
Exactly, the cylinder set is the following: that you start with anything, you fix any n coordinate in that sequence, and then you let the other running arbitrarily.
Yes. So
then the cylinder with respect to that.
I see.
So you fix that. You fix that n coordinate.
Yeah,
yes. For that cylinder set, you just simply
constructing probability measure of the infinite sequence of the experiment, and that's a Cohomology measure.
Exactly. And then you can start with the Bernoulli measure. Is exactly you multiply 1/2 with respect to n fixed coordinates, and this gives you the measure of that set cylinder. And because of that, cylinders also can generate the whole sigma algebra. You get finally the whole probability space and with respect to the Bernoulli measures for the whole space. And if that is the case, you can also consider the shift, which is a t here. The transformation is that you start with x1, x2, and x3, and then you shift to x2. So it's a Bernoulli shift. So this is an example of an ergodic dynamical system. Of course, we are in this case working with discrete time set. But you can also consider something like you start with another example on you have the unit circle, and you know that if you take any rotation with respect to any rational angles, then of course you will have periodic situations. But if you start with irrational angles, then you can expect that after infinite time, the image could be then set of the unit circles. And this is another example of ergodic transformation. Now, there's two criteria to work with the ergodic situations. The first one is a very famous theorem, which we call it ergodic Birkhoff theorems or Birkhoff ergodic theorems. So you start the following. You start with any f, which is a test function, is supposed to be integrable. and you work with a theta, which is ergodic dynamical systems in our probability space omega. Now we can claim that the ergodic Birkhoff theorems claim that for almost surely all the trajectories omega in the capital omega, the average in time of the test function f, which is the left-hand side, and if you take this limit for the time tend to infinity, then it would have converged to the right-hand side, which is the average in space. And this is respect to our p, and this is well, because of our definition, p is theta invariant. That's only true in this case. But this is often the scenario we have to assume in many applications. But I want to draw your attention to the second one, which is generalizations, which is of course a very important one, but often is neglected in many courses on dynamical system. This is the generalization called the Birkhoff-Khinchin theorem, which is proved later by Khinchin. And this is very beautiful. It's the following: you can forget about the ergodicity assumption. You just start with any transformation t, which is supposed to be invariant under p, and then you do the same thing for the left-hand side, which is a time average of the test function f. Then it would converge to the right-hand side. Normally, you can prove easily that the left-hand side it has some limit. Normally, you can prove this, and the limit is invariant under t, under theta. But to check exactly what is this, it is the right-hand side. The right-hand side is very beautiful. It is that the right-hand side of the limit is the conditional expectation of f, but condition on the sigma algebra of own invariant set of our transformation t. So this is a very generalized theorem.
So that Birkhoff-Khinchin theorem is a generalization of Birkhoff ergodic.
Exactly, because you can check, for example, if you assume further that theta is ergodic, then of course you can check that C, which is the sigma algebra of only variant set, is a trivial sigma algebra because it consists of an empty set and the omega. So the conditional expectation turned out to be the expectation itself. And so so there's no omega here in the right hand side. It's constant everywhere, almost everywhere. And that's, we will go back to the classical ergodic Birkhoff theorems. But you can see that here the ergodicity is neglected, and it happened in many applications. You see that, for example, the Poincare-Hopf bifurcation theorem, which you have the existence of one fixed point and also another periodic orbit surrounded by the fixed point. Then you have a scenario of two, right? Because you cannot say that it's ergodic because it has two fixed or stationary distribution. But then you can easily form that that's the sigma algebra C, and then you can apply that Birkhoff-Khinchin theorem. And this is a scenario that happened many times in dynamical system theory and also differential equations. And just to say further, I highlight here that the right-hand side is depending on omega because it's a conditional expectation. So it's actually a random variable. So that's all for the basic facts on the ergodicity of any metric dynamical systems. So now I have to go a little bit to the complicated situations, but it's also very trivial from the field of stochastic calculus. So I suppose that because Van told me that I should speak somehow something which is understandable to the whole audience. So I start with a very trivial example, which date back from Birkhoff times when he's working on stationary, on stability issues. So he has his thesis on stability of motions. His PhD thesis on that in 1892, and then this turned out that the concept of asymptotic stability for any deterministic dynamical systems since the Leibniz time, because he invented two methods. One is called Leibniz exponents, and the other is called Leibniz functions. And two concepts are very fruitful in studying the stability of any fixed point or any limit cycle or any object like attractors of any type of dynamical system, which is deterministic. Later, it is generalized to the stochastic scenario, and the work, you can see the work by Kaminsky in 1979, which is a very also classical book on stability of stochastic systems, and also later by Skolkov on 1997, and many others. And regarding to the stability concept, there's many work in terms of quantitative criteria for defining exponential stability. For example, Molchanov or Ludwig Arnold or Etienne Bardous or Baxendale or Solomon, and so many others in control theory, for example. So let me start with a trivial example, which is equation 1.1. So you imagine that you start with any matrix A, which is negative definite. By definite it means that you start with this kind of system. It would finally exponentially going to 0, and then you perturb this by some nonlinear function f, but still in the deterministic equations. So then you have A acting on yt and then plus fyt, and this is for the drift. But then you also want to perturb the system a little bit by another stochastic noise, which is any function g, very small, but then with respect to the noise here is any Brownian motion, like y noise. So you are in the scenario of applying the Ito formulas, because you have to work. First of all, you have to understand what type of equation 1.1 it should be, and this can be solved, for example, with the Ito theories on stochastic integral. So you suppose that you have to understand the equation, which is in the different form here, differential form here, by taking the integral. So you would have yt equal to integral of the drift and the integral of the diffusions. The drift is easy, right? Because the integral with the drift is exactly the Riemann integral. But the second one, the integral with respect to dBt, should be understood in the Ito sense. This means that you have to work with yt, which is in L2, so any square integrable, and you have to define the integral with respect to any standard prime motion bt, and you define the Ito way. So it means that you have to construct a sequence of simple functions, which is constant pointwise, and then you just working with a Riemann sum, and then you suppose that in the limit it would tend to something which is a stochastic integral. Now the Ito theory has a very, very fruitful consequence, which is Ito formula. It means that if you start with equation 1.1 and suppose that you're working with the Ito calculus, then actually you can compute the derivative of the norm of yt, or the norm square of yt, and this can be done as the following. You take that derivative here, supposed to be this one plus this one. This is normal derivative if you take any type of this form. But then you have to consider also bt here, because you know that bt is standard prime motion. So you have to add some more term here due to the effect of the stochastic noise, which is the norm square of gyt. And this one go to the drift of the transformation. And for the diffusions, you have yt, the integral, the inner product of yt and gyt. Now, in this scenario, you see that with our assumption on the negativity of the A, and the assumption that F is Lipschitz continuous with some CF here, G also Lipschitz continuous with some constant CG, then you can write down that this drift is smaller than this one. Sorry, probably it's here is redundant, so I made a mistake here. There's no GT here, but it's supposed to be DT here. And then the right hand side, this one. Now, the nice thing of the Ito calculus is that if you take the left hand side and the right hand side by the expectation, then the thing with respect to dBT would be ruled out after the expectation. So the expectation of that is 0.
Can you explain a little bit in geometric language for me? So asymptotic stability for deterministic systems, that means you have some
limit circle, or
yeah, so
in this case it's only a fixed point.
Yeah, so, fixed point, or even
yes.
Periodic system.
Exactly, but in this trivial example, I would suppose that 0 is a fixed point, the only and unique fixed point of the system. 1.1.
And then and then that is very geometric. Then you
yes.
go to stochastic stability. What is the geometry of the what picture I see?
So if you start with this, you can expect that any solution starting with any initial point would be converged exponentially to 0. So you start with any, let's say, a box, then it would collapse to the fixed point. So fixed point is also the unique attractors of the
attractor. Yeah.
So it's shrinking to only a fixed point. Now, exponential stability also tell you that if you are in this scenario, then if you also perturb the system from the beginning, which is A plus F, by some stochastic force like dBT, then the new system, the perturbed system, also converges to 0.
Yes.
Very quickly. And here's the proof. The proof is that if you're taking the Ito formula, then the right hand side would be written in this form, and after the expectation, this one is cancelled out. So in the end, you have this one. And you see that this is exactly the Von-Van lemma. And because of the Von-Van lemma, you can say that, well, the expectation of y_t squared would be exponentially going to 0. And then the rest is that you apply the Borel-Catelli lemma. If you say that, well, if they have the expectation go to 0 but exponentially, then every trajectory is also going to 0.
So stochastic stability is a kind of expansion of the deterministic stability for deterministic system, and
that's right.
Exponential stability is a rate of convergence.
That's right. So to say a little bit more specific, you should start with the scenario of defining the stochastic stability, which dates back to Kaminsky.
Yeah.
And so you start with this equation 1.1. You have to say that, well, the system now depending on t, of course, the solution depending on t, but it also depending on omega, which is coming from the Brownian motion. So you have to, first of all, construct a probability measure, a probability space in which Brownian motion is acting. And then you start to write the equations and then solve the equation. So you say that the solution is dependent on t, but it's also depending on omega. So it is a stochastic process. So in that sense, you cannot say that, well, Lyapunov defines the stability with respect to the deterministic system. But here you are in the stochastic scenario. So you have to work with t, but also you have to work with omega. So there's many concepts then raising, right? Because it's type of conversion. You would say that, well, I would have the conversion in almost Gaussian. So every trajectory has to converge to 0, right? This is also one concept. But you also say that, well, but you are in the stochastic scenario. So I can also invent the concept of stability with respect to the probability, which is corresponding to conversion in probability, right? It's also have a conversion with respect to the exponential, or a conversion with respect to expectation. So then you see that there's many types of conversions in dynamics, which is date back to the concept of conversions in types in probability. And then of course it means that you have to study about the dominated Lebesgue theorems, or you can say that when the almost sure conversion lead to the conversion in expectation, and so on, and so many things like this. But here we are in a very trivial example. So this is an exponential conversion, and exponential is important because it means that when you are in the exponential stability, you can assure about the stability respect to the almost sure set, and also is in the sense of expectation also. Yeah. But
so moment approach is what you should explain next.
Yes.
Okay.
Yes. So this is an example, but here I point out two things. The first one is that we are in the situation of applying the Ito calculus, which is BT. So you have to define the equation 1.1 with respect to the Ito theory. The second point is that what is implied here, what is hidden here, is that you have first to construct a probability space, right? Which is not our thin air, right? This is, you have to construct it in a very specific way. And for the first point, this has come to the question in the last slide, which I said that this is also my interest in several years. That what happens if you start to perturb the system with something which is not standard Brown motion, but something like fraction Brown motion, or any type of Gaussian noise. And it might have memory, it might be not independent, it's not Markov, and so on and so forth. So this leads to, of course, a generalization of these problems, which I would expect to tell you in the next slide. Now, you see, in the previous slide, I talked about the standard Brown motions. Now I talk about fraction Brown motion, which is, of course, a generalized concept of standard Brown motion. So you often work with fractal dimensions. You often work with something like self-similar process, which did to Mandelbrot when he's working with self-similar structures like Zulia set or Cantor set and so on. But the fraction Brown motion simply, in a nutshell, is that a continuous Gaussian process with center at 0. So BH of 0 is 0. And it has some covariant function like this. So if you think that this is too complicated, you simply take the expectation of BT minus BH, and then you take the square of this. Then the result would be T minus S to the power of 2H. This is the expectation. So when you see that when H is 1/2, you go back to the situation of standard Brown motion. So that's why when H is varying, you have the generalization of the so-called fraction Brown motion. And there's also a very beautiful representation theorems by Mandelbrot and Bannes in CTH, in which they prove that if you start from any standard Brown motion W, and then you can construct a fraction Brown motion following that formula. So you start with some constant CH here, and then you just following that formula. You can get the right hand side is a representation of fraction Brown motion. There's another theorems which is also a property of fraction Brown motion. It is a Kolmogorov chain. It says that because of the expectation is T minus H to the power of 2H, it means that almost surely all the realization of this fraction Brown motion is Holder continuous, which means that this one belongs to the Holder space. And in fact, it's belong to something a little bit more regular. This is not only C beta, it's 0 beta, which means that if you get the terms to 0, then the norm of the beta norm, beta Holder norm is also 10 to 0. And an important properties of fraction Brown motion is that it's not Markov process, and it's not even a semi-martingale process. So in other words, you cannot simply apply the Ito calculus into that quiet equations if you perturb it by fraction Brown motion, because it's simply inapplicable. So you have really to define some or invent some calculus to work with this type of noise. And this is exactly Rappa theory, which is dated back to the alliance in 1998, and further works by field medalists Martin Hires and others in this field. So here, normally I'm working with such type equation, but I'm going very quickly, so you don't have to bother too much about these things. So imagine that you go back to the situation. You go back to the situation 1.1 here, but this is the first time when you apply the Ito calculus. But in the next slides, I will simply invent a different method to tackle this issue. And this is the following. I would write it in terms of, how to say, this is the variation constants formula, which is simply you write in the integral form. You can prove that starting from equation 1.1, the solution can be written in this form. And this form, it is, of course, it's a semigroup because phi t here this is a semigroup of A. So is this the generator? A is generator of phi. And you can write this way. And then since because of that, you simply taking the norm and then you apply the triangular inequality to get that form, right? And because of the non-negativity of the negativity assumption of A, you can estimate this Vt, the norm of Vty here by this one, which is of course exponentially decaying to 0. This form also can be estimated. The only thing that is not yet estimated is the stochastic integral, right? And but for this moment, I just simply take it into Bt, so it's any type of perturbation. I call it Bt, beta t here. So this is you can call it a like stochastic perturbation. Now I let this beta acting as like any type of time varying functions. Now I'm looking simply this is type of inequality. So you have yt in the left hand side smaller than this one. Now then you can, after some transformation with applying the continuous one-one lemma, you end up with something like this. So yt with respect to e to power lambda t is smaller than this one. So now you can see that, well, in the inequality 1.4, you have this thing, you have this thing, you have this thing. Now this is the beta t coming to place, which is a stochastic noise or stochastic perturbation, right? If we are in the situation that the perturbation is 0, then we are done, right? Because this is 0, 0, and then you have the exponential stability. But of course, this is a stochastic integral, so it's not 0. Then you have to take now the expectation in the both side of the equation, right? So you apply the expectation and you apply the isometry of the integral. You can see that, well, if you take the expectation of beta t square, then you can estimate it as the right hand side. Yeah. And this is the rest is that when you get that and several technical things, you end up at that things. So you end up at saying that, well, there would be a situation when you can apply the one-one lemma, but for the integrated integral like this. And you can say that, well, you can estimate some lambda, estimate some positive root. So it's another parameter which is systematically invented. And then you can say that, well, if Cg, which is the noise or the intensity of the perturbations, G, is smaller than this one, so that is inequality 1.8 is whole, then you are in the situation the stochastic stability. And this new method is what I invented last year, but of course it can be compared to the classical method because this is turned out to be just a difference with respect to one type of constants. So it is quite the same. But why is this, I call it pathwise approach works? I would say that here the pathwise approach works until you have to apply this one with respect to integral. And the idea is that until here, everything is still deterministic. But after 1.4, I start to act on the expectation operator. So this starting from this step, everything can be generalized. And that's why when you apply this type of technique into the fraction bar motion, then it's also work.
Children, why is it equality you call that isometry?
Isometry of the integral, because you see, if you take this one, then you take the expectation, then
Yes.
simply the dbs square would become ds. So you see that on the left hand side, you have the integral with respect to dbs, but of course it's the norm square, right? On the right hand side, everything would be included to the norm square, but then with respect to ds. So all the noise after taking the moment about the two would be translated into any type of Riemann integral, but of course with respect to the expectation in the integral. Yeah. So that's why you have the integral, the expectation here inside, and the integral now can be understood in the terms of Riemann integral. So this technique often work when you're working with the expectation operator. Yes. But it, as I said, I point out that this is what I should emphasize. This techniques only work for the Ito calculus. Now, if you were working with stochastic, like fractional round motion, then you cannot simply taking the expectation on this and you expect that you will get an isometry. There's no result like this. There's no property like this. So it means that we have to start from 1.4, which is this one, and then you have to go in with other techniques in order to apply the system to the fraction round motion. Now I can do the following. This is the thing that I point out. So this method is that how can we apply this integral now with b, which is standard round motion, is replaced by the fraction round motion. How can you estimate it? And so this is the answer is you have to apply the Rapat theory. You have to apply Rapat calculus to do this. It means that you have to define what is a stochastic integral with respect to BH here, and then you have to apply, have to estimate the stochastic integral with respect to the norm in p bar of this yt here, and of course with respect to some function x here. I will explain later, but the idea is the following. Once you can explain this, you can estimate 1.9, then you are in the situations. Let's go back a little bit, one slide to 1.4, that you're starting with here, which is 1.4, and then you write it some way into this situation. So at the end, you will have the last line, which is the yt, the normal yt, but e to the power of lambda t. So this is something like exponential growing. The right hand side, you have y0, so this of course the solution is 0. But then you have some discretization. So you have t from 0 to n, but then you simply cut it into 0 to 1, 1 to 2, and then and so on. And then with respect to that inequality, you can apply the so-called the discrete Goldman lemma. And gt here now is here. G is some function of the p bar norm of some noise. Let's call it this way. And then et is included into u here, and then you have this situation. It's still very abstract, but then you are in the scenario to apply the discrete Goldman lemma. So in the end, you will have 1.13. And this is a very general method to work with stochastic stability and exponential stability, because if you take a log of that, right, and if you somehow can prove that the right hand side is negative, then it means that of course this is on average log is negative. It means that yt is exponentially decay, right? This is the result that we would like to prove. Right? But how can we prove that it's negative in the right hand side? This is the issue. Right? But you see here now you are in the situation. It looks similar like Nichob-Egri theorem. You see, because you have the log here, you have the sum from 0 to n minus 1, and then you have average over time, right? So this is a point that we have to apply the Birkhoff-Egrig theorem. But throughout all this presentation, I never tell you anything about what is a probability space, what is a dynamical system, so that you can apply the Birkhoff-Egrig theorems. This is the rest of the presentation that I would expect. So this is just a motivation example, so that I can persuade you that well, calculus going to that scenario of 1.13, in which from now on we have to construct a probability space, we have to work with the stochastic scenario, and you have to work with metric dynamical system. And yet it's not enough, right? Because we have also to prove the ergodicity. Because without that, how can you sure that this is negative, right? Because this is lambda, which is a constant. But the right-hand side, this second term is also, if you are, let's say, in the situation of Birkhoff-Kinsin situation, then even this limit is also varying with respect to a random variable. So you cannot be sure whether it's positive or negative, right? But if we can prove the ergodicity, then this is nice, right? Because it means that this is constant. So then you can control that constant to be either bigger than lambda or smaller than lambda. And then you can say about the ergodicity. So all such type of techniques always true until this step, that normally before that is doable and normally can be done. But the rest is always very complicated from the probabilistic, because it's a different techniques. So you have to construct the probability space. Yeah. Okay. Now the rest of the presentation, I will talk about how to construct the probability space, and this is of course the crucial point of this talk. So of course I'm speaking about it. I mentioned about w.r.t theory. I mentioned about w.r.t integral and differential equation. Right? So of course we need to construct some theory here in order to build the probability space later. So in the short form, you can expect that you're working with some finite space CP bar with respect to the norm here. The norm is the initial point, and the P bar semi-norm, which is this semi-norm. You can also working with the P bar norm, or you can also working with the Holder norms, which is this way. Normally, they are quite equivalent. But drop part means the following: you start with any realization small x. Now, imagine that it's not enough. You need to borrow some additional information from that. Think about a legal situation. You have only one line, but then you still to build something which is a higher dimension. So this is a capital X. Normally they call it Levy area. And you can think about this as the following: if X is the C beta continuous, then the capital X has to be higher regular. So it's a C2 beta. And the relation between small x and capital X is the chain relation, which is equation 2.1.
Each chain. Each chain here, he's working on how is you call that the chain relation.
Yes, this is a chain relation. But the chain relation is just relation, the identity 2.1, which means that if this is a two parameters flows, so you have to with xst minus xsu minus xut is equal to su and tensor multiplication with xut. But you can think about it, that's an example is here. So symbolically, it is written in this form. So it's the integral of xu minus xs dxu. What is this? You can imagine like this. You have a situation of a triangular, like geometry. You have a triangular.
Yeah, so that's not chain integrated part, integrand or that another chain. So
yes, so you shift a little bit. So this is the area for the whole triangle, which is a big one. Then you take in any point, you go into parallel to the one axis and you go the other axis, right? This is creating another smaller triangle. This is XU and XT, UT, right? And if you simply take the difference between the big triangular and the two small one, you get the
Yes.
rectangle.
That's my question. That is, yeah, that is change from stochastic analysis of chain geometry.
I don't know, but
okay,
that may be true. That it may be true because Trent is actually working with iterated integral. His work, I mean, is from very Stone Age, like 19 something. But I guess it's true that this is the motivation is from chain relation that Terry Lyon started to work with this Rappa theory, which is the chain identity, and then he applied it to some form of stochastic integral or rough integral with respect to any regular or lower regular x here. We call it Rappa x. So, but think about it as a following. This is two examples for you. The first one is, this is two stochastic example. The first one is you are working, go back to the Ito calculus, right? You have any AS, let's say any square integrable process AS, which is adaptive to the sigma algebra and respect to filtration, and such that this integral Ito calculus exists, right? Then you can think of the capital X here at this form, and actually it can be computed explicitly like xt minus xs square and then minus this form. So this is another form of this. As a second example is that, let's say you're working with the fraction of Brown motion, and you know there's a same many way to define the stochastic integral. Either respect, let's say the simple way is with respect to score integral. So you have this integral is understood in the score form. So you need Maillard-Bank calculus to understand this, and you should suppose that this is another stochastic integral. But in this scenario, you can also compute it. You can compute the Levy area x here explicitly as this form. Of course, using some complicated theory in terms of weak in the product, so many other things on Gaussian processes. But then you can prove this. So this is two examples, trivial example to show that well. Practice, you can apply any realization of this stochastic process coming from any type of stochastic integral here, and then it fit to the chain relation 2.1. Now, suppose that with that you can define the stochastic integral in the pathwise sense. It means that you simply start with any y, which is the beta continuous, and x is beta continuous, which is Holder continuous. If beta is bigger than 1/2, then you can even define the Young integral here by simply taking the Riemann sum of this form, and then you let this partition tend to 0, the grid of this is final, and then the limit would lead you to a type of Young integral. But the other thing is that if you are in a situation of lower regularity, let's say beta is only bigger than 1/3, but smaller than 1/2, then you can also define the stochastic integral, which is my pointer here, which is you can define I call it rough integral, and this is a definition by Guvinelli. How to define that? You have to add more information from x. So in other words, you have to lift small x here to our black capital X here. And what is black here? You see this is black. So you start with x small, you add the Levy area with capital X, you have the black x small. And then this one is turned out to be, you extend the dimension of knowledge to another thing in order to get the black x. And then you get this also the Riemann sum of this right hand side. And with other stuff with this, you can say that, well, this integral also exists. And this satisfies some properties here. And this is how we define the rough integral. Now, once you can define the calculus for that, which is a rough path theory, then you can basically define the equation 2.2. Now you're in situation, right? Because then you would say, well, we have the equation, which is yt equals y0 plus this thing, fys ds, very deterministic. Right? Now, if you perturb the system by something which is, right, let's say x here is the fraction of ground motion, then applying w.r.t theory, you can say that, well, this integral, stochastic integral, can be written in the form of w.r.t theory. So this is a rough integral. This means that you define the integral, you can understand this equation in the integral form, then you have to solve it, right? You have to prove the existence and uniqueness of the solution, and many other classical results of this. Once you prove that, you have to say that, well, how can you generate this type of equations to some system like random dynamical system? Right? This means that by random dynamical system, I only speak about this in the last visit to your institute about random dynamical system. But I repeat it here that it's simply a measurable functions on our omega metric dynamical system, which is omega fp and respect to our theta t.
Đức Anh cho NDS dynamical system N. What is the N here?
N is non-autonomous, but it can be random. Sorry, should be random. So
only the random dynamical system is a
yes. This is a random, and it certifies that you start with the cocycle property 2.1 here should be understood in the geometry wave here. So you start with x, you go in s time, you end up at this fiber theta s omega, right? And then you go in from that point theta to another fiber, right? Then going this way is also the same result, and you starting from x, but you go in t plus s time, you end up here. So simply it means that somehow it looks like the existence and uniqueness theorems in solving the equation. Right? You go in showing this form, and it's showing another form, or you showing the whole interval. You should have the same result. So this is, you can understand that cocycle property lines. Yeah. But if you have a random dynamical system, it means that, well, it is hidden here. You need an ergodic dynamical system, you see? And, well, this is the whole thing, because then it means that, well, okay, we have a rough differential equation. You have to construct something like a ergodic dynamical system with respect to that. So the crucial point here, you come back to how can you construct this metric dynamical system? And here's a construction. It led back to the result by Paleo and Sebastian Vito and McCann Choice of they will believe. So the issue is that you remember here, this is our small x and capital X, which is our rough part. We certify the chain relation, right? So somehow from the chain relation, we have to invent some group operator, which I call it bullet here, such that this identity is whole. If we can prove that, then somehow you already extend from small x to the whole set, right? And then you can talk about the flow. And this is the bullet operator can be defined easily here. So you start with something like a tensor product, which is a set here. So you have 1 and r, indirect sum of im and the tensor product im square. For this set, you simply take the 1, which is the first coordinate is always 1. The second one is g belong to im. The third one is in im square. Now the operator is that you equalize it. Think about it, and you multiply 2 polynomials, right? Think about it as a polynomial 1 with order 1, order 2, and order 0. If you multiply that, this is a g1 is g2, simply the coefficient of this order 1 and order 2. Well, you end up at here, right? Yeah, 1 is still the free coefficient, which is 1. But then g1 plus h1 is, of course, because you are in order 1. The same thing with order 2. The order 2, you have to multiply g1 plus h1, which gets it here, and g2 and h2, right? This is the whole thing on operators. But let's think about it. If you replace g1 and g2 here by x su, and then H1 and H2 by X ut and capital X ut. And then you apply the chain relation here. This is exactly the left-hand side of this equation. This is exactly 1 x st minus x s and capital S x of s from s to t. So in other words, if we invent that bullet operators, this is a group topological group with that unit elements, and from that group you can start to invent the co-cycle flows into that. And so the rest is that you have to invent the compact topology, compact open topology for that value, the space, which is T2 here. So you simply define the matrix, which is between two rough paths, x1 and x2, by this form. This is compact open topology. And then you just have to work with the C2 0 beta 2, which means that acting on T1 2 here. This is our tensor, right? T21 here. And then you acting on that, you invent that C2 0 beta here. Then you define also the theta, which is a Wiener shift at this form. Now remember that before that we have many examples on Brown motions, which is the operator here simply a plus or minus operator. But because we are in the T2, this is a tensor space. So it means that you have to work with the bullet operator. But still, it is a group. So you can talk about the inverse elements of omega t and this one. So somehow the shift type of Wiener type shift is quite similar, but the only difference is that instead of plus operator, you have something like the group operator here, and instead of minus here, you have the inverse elements of omega t. And this is the only difference. So once you get that, I mean, the authors like value and Vito and Choice-of, they already proved as well. If you're acting on that, you can construct a rough path cocycle, which is Holder continuous, like this one. So for each omega small in this omega probability, you have this turn out to be the realizations, right? And this realization is exactly our rough path, small x. And it certified this form. So, well, then we are done with this construction of probability space. Yes. I cannot hear you. I cannot hear you. Can you unmute it? Sorry, but I cannot hear you.
Sorry. He had question about the biological meaning of ergodicity in the stochastic epidemic model. Did you do something like that?
Yes, yes. I can say this. By ergodicity in the stochastic system, there's two meaning. I mean, first of all, ergodicity, when you talk about this, it's correspect to the concept that I already present. But in many applications, in stochastic theory, like epidemic, or in social science like economics also, or finance also, ergodicity sometimes regarding to a macro process or any type of stochastic process. It means that normally there exists a unique stationary distribution, because let's suppose the following: you have a macro process, then you also have you can generate a Markov semigroup for that. Then normally, if you have assumed about the tightness assumption, then you can say that there always exists a stationary distribution. But you cannot assure that this existence is unique. It can be more, 1 or 2 or 3 or so on. So you need to work further, and you need another assumption on irreducibility of this process. And once you get that irreducibility of this of the tightness of the equation, then you can prove that then there exists only unique stationary distribution. And of course, because it's unique, it's automatically ergodic. So that's why in applied science like physics or economics or economics, sometimes ergodicity relate to the existence in uniqueness of stationary distribution. And that's the only thing, the difference. hope that I answered the question.
Yes. So if okay, if you have question, can just raise
Yes.
hand or
Yes, thank you. Just feel free to ask.
yes.
Okay, so I already show you how to construct the probability space. So the rest of the talk is mainly to prove the ergodicity, which is also the most difficult part. So I have to admit that, that in general, there's no algorithms to prove the ergodicity of any type of stochastic process. But luckily, we have a very specific scenario in which if you're working with something like fractional Brownian motions, so if x in our case is stochastic process turn out to be a fraction Brownian motions, then we can conclude that our constructed metric dynamical system is ergodic. And I think that I expect that the same result is still true if x is Gaussian process. So it is not only fraction Brownian motion, but any type of Gaussian processes. Then we still have some hope to prove the ergodicity. But let me simply focus on the situation when x is fraction Brownian motion. So classical result when you're working with standard Brownian motion, it means that h equal to 1/2. Then you can easily construct the probability space by taking omega here is our space of continuous function, right? So it's C0, and at 0 it's equal to 0. So it's C0 up and also the sub is also 0. Then you have the sigma algebra, right? It's compact. It's generated from compact open topology, and also you can construct probability space with respect to some canonical process. Here is a standard Brownian motion. BT is canonical process, and P1/2 is simply the Wiener measure. And this is proved by some result you can take back to Bobsler that there exists a Wiener shape. The Wiener shape can be easily defined like this. So you're taking omega for every, of course, the continuous function. So omega at some point s, for example, equal to omega t plus s minus omega s. So simply you shift it. Sorry, maybe I make a mistake here. So it should be omega t plus s minus omega t. Sorry, minus omega t. So then you can prove that this is a Wiener shape is ergodic. This is a situation with standard Brownian motion. This is long. It is known from 78 and also addressed to in the books by Ludwig Arnold on random dynamical system. But to prove it for fraction Brownian motion takes some works, and this it should be do the following. You simply transform. You first have to construct this metric dynamical system. You have with omega here. You have with the Wiener shape here, and with respect to the Wiener measure P1/2, and then you simply construct BH following the Mandelbrot-Vaness formula, which I showed you in the previous slide. And we still keep the Wiener shape like this. The Wiener shape is still the same with BH. But then you need to work with a fraction Brownian motion and also with respect to pH here, which is the transformation. And that, this is also the classical lemma I showed in the first slide. We state that, well, if pH here is a measure of transformation, and you have a situation that P1/2 is ergodic, then after the transformation is also ergodic. So that's why you're in the situation that to say that pH is also generated ergodic dynamical system. But remember that you are still working in the scenario that the operator here is at xt minus xt. So it's still like a plus and minus group operator. It's not yet like a bullet operator. I show you with respect to when you're working with the tensor space. So to do that, you need to follow the following. You start with that in the basic small x. Then you have to extend that. You have to lift that small x to rough part, which is of course belong to our C beta 0 space. This is a Banach space, but in the tensor values, which is T2 1. And from that, you have to apply several important results. For example, Fritz and Victor. You use the piecewise linear approximation, which is a polyfier approximation of the path by some smooth curve. Then you end up with this something like this. So this is, you have to lift that on the smooth curve, because this is still C2 beta. It is it contains many smooth curves. So it means that for smooth curve you have to apply the natural lift, which is ST here. For X is smooth. Then you can define that integral, because X is smooth. It is simply like C1. And so this is turned out to be Riemann stringent integral. Then this is well defined. This is well defined. And so this is a natural lift of S. Then you take that natural lift of S, and after some limitation approximation, you can extend it to the whole space. So you embed that thing into the larger space. And then the rest is just apply the previous lemma on the transformation, right? So you have that S, which is a measurable transformation. You have pH here, right? Because pH is this one, is ergodic. This is, of course, the transformation. If you say that, well, this is ergodic after the transformation, of course, P hat is also ergodic. But this is the whole thing. The rest is that you're checking for equal dt 3.4, which to say that, well, you can somehow, in a sense, complete the whole space after the limit process, limiting process. So it's mean that, I mean, this is tough technique to transform from the ergodicity of the first line, which is standard Brown motion, and then after the transformation to the fraction Brown motion, following the generator of Mandelbrot and Van Ness, you get the ergodicity of pH of the fraction Brown motion, and then you embed it, all the things, after Rapat lift into a larger space, and then you introduce a natural lift S. You prove that everything is measurable into the new space. You prove simply that this is, with respect to that type of probability, it is invariant, and then the ergodicity automatically come out. So this is how we prove the ergodicity. Yeah, and so this is the thing. So, as I said, this is the fact that once you have the ergodicity, then of course you can prove the 3.5, right? Because this is simply the consequence of Birkhoff ergodic theorem. This means that you can take anything with the p-bar norm of X, right? So between S to T, you just ship it, and then you get that. This is exactly the situation of the Birkhoff theorem. And then simply because of ergodic, it's exactly the expectation of this one, which turn out to be constant. And once you get that scenario, you can apply all the things to study the stochastic stability of the stochastic system. Yeah, so with that, probably I should stop the presentation here. The rest is simply that I apply it to generalize my situation to the existence of random attractors, and apply all these theorems. So I start with something like this. This is a drip. This is a diffusion. But now you're working with any type of noise. You assume about the distributivity of the drip. You assume about some noise. Then you can claim that there exists a random attractor to this, and also the attractor also converges to the deterministic attractor if you taking the control perturbation to 0. So the smaller the noise, the closer the random attractor to the deterministic attractors. And not only that, you can also making the system discrete. So you study the numeric solution of that. You can also prove that, which is in the secularized side. This is a very recent result in December. We can submit to a journal in the field. We state that if you're working with discrete situation, you already borrow the ergodicity of the metric dynamical system. Then you can prove that even the discretizations of the stochastic scheme also converge, and it's also admit a numeric attractors, and the numeric attractor also converges to the real attractor if the step size of the discretization tend to 0. And that is I quite like this result very much, but it's very applicable in real application later. So thank you for your attention.
Thank you very much for the beautiful talk and the expense very impressive present. You can speak out, yeah. Ben Lahib Adesat has the question. How can I prove numerically that a given stochastic dynamical system is ergodic? That is, are there any specific spatial graphic or simulation to determine whether a system is ergodic or not? Yeah.
I doubt that. I mean, this is very good questions, but I doubt that we can prove something ergodicity easily by simply numeric simulation, because I mean, normally the Birkhoff ergodic theorems give you a criteria to test. So let's say you start with a time series of impure data. Let's say anything like stock price or anything like that. If you suppose that you're working with the average, right? You take in time. If you're in the situation, we can apply that this is ergodic. This means that by definition, right, and by Birkhoff ergodic theorems, the average in time would converge, right? It's converge to the expected in space, right? So it means that you just going let's just time length to infinity, or let's make it to time large, and checking whether this time average would convert to something, and it's turned out not convergent, then you can say that, well, somehow it violates the ergodicity. This is the only thing that I have in mind, that how to check the ergodicity numerically. But in principle, I doubt that there would be a criteria to test that.
What's the DCDS dynamical?
This is the joiner, discrete and continuous dynamical system.
Discrete continuous dynamical system. Yeah. Yes, that's how to say, a lot of work this year. APR already submitted. Congratulations.
Yeah, thank you. Actually, I did it even in 19th, but you know, because it's also a good journal, it takes time, like 1 or 2 years to get there.
Yeah, so good, how to say, COVID time to think about. Yeah, actually, that's a good time not to travel a lot. Yeah.
Yes, yes.
Okay. Is there any more questions? If there are no more questions, let's just thank the speaker again here.
Thank you.
And I stop recording. Yes.